Hello everybody. Now it seems that my microphone is again working. Are there any questions at this time?
Hello, sir.
Yes?
So my question is regarding the usage of the Smith chart in the theoretical part of the exam. How would we need to use the Smith chart in the theoretical part?
Well, I don't think you will need to use the Smith chart this Friday.
Okay, thank you.
So, we have something, a Smith chart, which is a good graphic tools to calculate impedances, admittances, reflections, and impedance matching. But we will learn that only a week later when you will have your Smith charts at hand. That's first point. Well, week later means in January this time. The second point, we will now switch to other topic to make use of our time. And the other topic is a waveguide. First, we will again switch back to the wave equation. A wave equation, just to remember, is given by Laplace applied on electric field E, vector phasor, plus k, the wave number squared, E, vector phasor is 0. This is the wave equation for harmonic fields and out of any location of sources. So without sources, just for propagation, this is the valid wave equation. Now, we have another set of equations, and that is for the magnetic field. Let's say for this intensity, we have another equation of the same form. And this equation is valid as well. Now, the problem with it is that we have three components of H and three components of E, let's say in Cartesian coordinates, that's Ex, Ey, Ez, Hx, Hy, and Hz, and therefore, in fact, this represents 6 partial differential equations. But it's important to know that those field components, although they are 6, they are not free to change, but they are bound, and in fact there are only 2 field components that are independent. You can establish the others by combining the Maxwell equations, so that what you need really is to know 2 field components and, well, 2 independent field components, which, for example, for a wave propagating in the direction of z, could be the component Ez and Hz. So those are really independent, and you can find out others out of these 2 components. This means that once there is Ez, it will give rise to other components. So the component of electric field strength, now I omit vectors and phasors at the moment, but this gives rise to magnetic field components, which would be H, X, and At the same moment, this would have, this means that you can't select independently EZ and HX because they are dependent on each on the other. But now you can find out that there are two separate fields that could exist in a waveguiding structure. One is derived from the EZ, the other is derived from HZ. And now different authors call that in different manners. So if you start with EZ, which is a component in the direction of propagation, then you would have only magnetic components which are bound by the cross section of the waveguide. So in fact you would have only HX and HY. Now if you start with HZ, you would get again two components, which would be E let's say EY, HX. Now this is something which has the electric field only in the direction of the cross section. So this is called transverse electric, or TE. So some authors classify this as transverse electric, and in our book this is done. Some other authors remember that that has been derived from the Z component of the magnetic field, and they call it H mode. And vice versa, this runs for the transversal magnetic modes that some authors called E modes. Now, not to result in a complete mesh, we will stick to the taxonomy used in the Hayes book. So we will use TE modes and TM modes, and especially we would now talk about the first mode, that is with the lowest frequency for transmission, which is the mode TE10. It is used that we write that TE10, this is not 10, this is 10, but we do not make any line or separation of those two modes, because a mode of TE10 is a nonsense. There must be two indices for a mode in a rectangular waveguide. Now what this does mean, in fact, if you have a TE mode and you have a rectangular waveguide, so we have a cross section of the waveguide, let's say described like this. So the first number tells you how many half waves of a sine is located along the longer wall of the cross section. So let's call that A, the shorter one let's call B. And now with this waveguide which is metallic, one knows that at the walls the electric field strength must be 0 because it is a tangential component at the surface of a conductor. So the resulting electric field pattern in the first mode is this. You have 1/2 of sine wave for the distribution of electric field at the longer wall. And you have 0 sine waves on the shorter one. So this is A, and this reflects to the number of half waves on at the B direction. This is the simplest situation with the waveguide. And before I will talk about equations for the components, I will try to show you a picture of 3 important quantities that form the wave propagating with the first mode of a waveguide. Now let us first see the distribution of the electric field. So, having a cross section, the electric field is formed by 1/2 of a sine wave, so its tangential component at the shorter walls is 0. It's maximum at the middle, and it again is dependent with the 1/2 of the sine. That this is the cross-section view. If we cut the waveguide in this manner, so in the middle, and this is the direction of propagation Z, we now would have the electric field, of course, this is the plane, it has been just maximum here, but remember that propagation along the Z is still bound by some maximum cosine beta Z, that's any propagating harmonic wave. So in fact we would have the field like this. So the just 1/2 wavelength from this place at this time we would have the same magnitude of the electric field but opposite sign. And this would repeat along the waveguide. So this is as to electric field description. Now, the electric field could not exist just by electric field. So again, we have the metallic box, and the electric field is accompanied by charges that are sitting on the walls of the waveguide. So we have some negative and some positive charge over here. And the electric field exists there. We have the charges. But that's not the whole. There is also a magnetic field inside the waveguide. And this transverse electric mode has 2 components of magnetic fields. In the direction of propagation and perpendicular to the electric field and the direction of propagation, which is the x. So we have the magnetic field which has this direction, but it is not just a vector traveling from some point to another. You know that magnetic field is composed by closed loops. So in fact those loops are somewhere around here. If I may draw it, so the loops are here. And then there are loops in the opposite direction. Well, those loops are closed, but in this view we can see only the projection of those loops which seem to look like a simple vector, but that's a rotating, not circle, but a rotating planar loop. And of course it's again in that way here. So there is a set of loops of magnetic field which are connected to electric field strength. And this has the third component, which is electric current flowing on the metallic walls of the waveguide. Now, how that happens? Well, if you have a magnetic field component inside, it also touches the conductive wall. Electromagnetic field does not significantly enter into the, let's say, metallic or conductive housing, so that we have a boundary between a conductor and the air. And at this boundary, the magnetic field must be accompanied by current flowing on the boundary. And the current must be perpendicular to the magnetic field. So we have a current that is flowing just in this direction. If I just put the upper deck of the waveguide over here, so we would have the magnetic field now projected not as just vectors, but those would be loops. This is the magnetic field just inside the waveguide, and on the lid or on the cap of the waveguide there must be a current that has fulfilled the boundary condition. So if there is a current that flows this way, it would create magnetic field of that way. So at the it would look like this. There is the current flowing to the center of the loop. And as there is just 1/2 of the wavelength, we have a loop that is circulating in reverse direction. There would be a current flowing in an opposite direction, so this current would be flowing out. And now you would see one current line that is just flowing from this center of the magnetic whirl to the other. So this is the upper lid, so this is here. Now you have seen some current lines that are going to the sidewalls, and as the magnetic field over here on the sidewalls is homogeneous and just going in the z direction, it has no y component, it must hold that the current on this side then flows to correspond with this. This is the upper deck, so the current must flow this way, and 1/2 wavelength it flows that way. The currents in the sidewalls are going up or down only. Just what is the practical use of that? Well, if I need to cut a hole into the waveguide, for example, to insert some measurement apparatus or some semiconductor, or just to have a hole which allows the air to pass through, I can cut it wisely in that way that it will not affect the propagation of the wave. which means also that it will not radiate. So if I use the shorter wall and I just cut exactly vertical and thin hole there, the wave is not corrupted by that because the current easily makes it around. But if I, for example, made a hole in this direction, then the current should do this. And therefore it will be traveling on a longer part, and it will be producing other components of magnetic field that were not contained in the original propagating mode. That would result in radiation or reflection inside and vice versa. So there is a way how to cut a waveguide's wall with the mode which will not corrupt the propagating field. If we need to make a hole into the wider side, this cap, we can do it also, but not elsewhere. In the middle, just in the middle, there is the current with only longitudinal component. So if we cut a hole, which will be a short slit over here, the current makes it easily around and will not radiate and will not change the propagation. But if we made something like this, that would corrupt the propagation or affect the propagation. So now I have drawn three components: electric field, magnetic field, and current. In fact, I have mentioned fourth component, that's the charge. And now let's tell the story about the wave that propagates through a waveguide. Well, first, let's start, for example, with electric field. The electric field, which is shaped like, let's say, a hill and a basin and a hill in both the direction of propagation and the cross-section along the longer wall. So this wave is traveling. Once you move this electric field, you get a change of the electric field against time at any location of the waveguide. A changing electric field strength against time means that there is also changing the, so we have E, and as it's moving we have a time change of the electric field. And this, of course, means that there is a time change of the electric flux density. But a time change of an electric flux density is called a displacement current. And the displacement current creates magnetic field. So this gives rise to magnetic field. As the time change here is not constant but is harmonic, also this magnetic field is changing against time. So we would have a time derivative of the magnetic field, which of course means that there is a time change, time derivative of the magnetic flux density. And as you know, a change in magnetic flux density means that there is an induced voltage E. And we have gone through the whole circle with electric field strength and magnetic field. So the electric field strength time derivative produces magnetic field, and the magnetic field time derivative produces electric field, and that's why the whole phenomenon here can happen. But it behaves a little bit differently from a plane wave, because this is the story for a plane wave. Now we have to talk about the boundaries, that is the walls of the waveguide. Well, first, I have mentioned charge. There is some charge sitting, positive and negative, sitting on the walls, and that charge, of course, is responsible for electric field strength, which runs from the positive charge to the negative charge. Now, the magnetic field inside creates currents in the walls. But a current is something which is moving charge from one location to another. So this moving charge then appears, and we are also, due to that, moving the conditions on the boundaries so that electric field, magnetic field, charge densities, and currents are moving synchronously with the velocity of propagation along the waveguide. Now there is a short question which is always asked by students, so I will reproduce it. I do not expect you to illustrate this whole story when I put down the question about the field distribution in a waveguide, which is one of the basic questions, because it took me some 10 minutes at least, and you have some 90 seconds to do that within the written part of the exam. So it is important that you know and put down the equation or draw the picture for the cross section. So for example, if you draw something like this, which is the E field described by half sign, this is the direction, this is the magnitude, then the magnetic field that are circles in this way, and you should or could also add the currents. It is not needed to draw several projections because you do not have much time. Just if that picture somehow resembles the propagation, I'm happy. You may expect that I can ask within the oral part for more details, then we have time enough. But just, I do not want you to be Picassos nor Dali. You do not have to produce a very nice picture of the waveguide and the mode. You just have to sketch an idea. Now I have been explaining something which is not very easy to understand, and I expect your questions.
Could you just please retell about the current direction on the first sketch, the upper one?
The upper one, yes. So the important point is that the current must be, well, I used the green line, the current at the metal surface must be perpendicular to the magnetic field, which is the boundary condition, as you remember. Well, this is the plane current density, and this is the magnetic field intensity at one and the other side of the interface.
Okay, thank you.
So just, it is important to find out the direction, which is this in this case, and that's it. Are there any more questions? Now, I will use, normally I would have prepared, or no, well, in normal conditions, at this point I stop the lecture and take you to a lab where we have a number of waveguide components. And I would show you and describe the electric fields inside, which describes a waveguide in the best manner. But at the moment I can't do it. What I can do is I can film a short video, which I would do. Unfortunately, I have it only in Czech at the moment because I expected to prepare it till next week, but we have somehow rescheduled that. So you can expect a short video from a lab. I will always take a waveguide component, describe the directions of fields, and tell you why this is done that or that way and how it works. Because that somehow helped me when I was approaching the problems of waveguides to understand that it really works. It's a difficult topic because so far you have been told that electric circuit needs two conductors, a positive and a negative one at the beginning, which lead the current, and that's the electric circuit. Now we have something which is only one conductor. And that's it. So, if I may, I would refer that to a video that I will first put on my YouTube, and second I will send you a notice into this Microsoft Teams. As a short comment, there has been a big dropout in YouTube services yesterday, but it seems that everything works now again, so you can again access my videos. It seemed on Monday that they are not there, but at the moment it works again, so you can use it, and hopefully it will work during the examination period so that you will be able to replay my lectures that have been put there. So, are there any questions at the moment? It seems that both you and myself have the right for another 5-minute break.